Hello everyone and welcome back. In this video we're going to introduce a special type of model called sampling distribution models. Instead of working with the original population, we want to focus on the values of statistics such as sample means or sample proportion. Let's consider a population that has a population proportion P. Now suppose that we were to take not one, but many different random samples from that population and then calculate the sample proportions P hat for every sample. We should expect that the sample proportions will vary from sample to sample, and this variability is called sampling variability. So for example, suppose that we tossed a fair coin 20 times and then we calculate the proportion of heads that occurs. On one occasion, we might see 9 heads, which will give us a sample proportion of 9 out of 20, or 0.45. And on another occasion, we might see 11 heads, which gives a sample proportion of 11 out of 20, or 0.55. And so the sample statistic will typically vary from sample to sample. Now we can model the variation of a sample statistic by using a sampling distribution model. So here we will imagine taking every sample from the population and then we calculate the sample proportions for every sample. And so the distribution of all sample proportions from every possible sample of the same sample size is called a sampling distribution of the proportion. Let's look at an example of a sampling distribution. Suppose that a random sample of 3 people were asked whether they preferred Coke or Pepsi. Let's assume that half of the population prefers Coke and the other half prefers Pepsi. So let's find the sampling distribution for the sample proportion that prefers Coke. So here are all of the possible samples that we can obtain from 3 people. So capital C indicates that they prefer Coke, and capital P indicates that they prefer Pepsi. And so for each of these samples, we can calculate the proportion that prefers Coke, which is given by this column. So now we can look at finding the probability for each sample proportion. And since we assume that half of the population prefers Coke and the other half prefers Pepsi, then each outcome will be equally likely. So for equally likely outcomes, we can determine the probability by taking the number of outcomes over the total possible number of outcomes. So here there are 8 total possible outcomes, and so now we can calculate each of these probabilities. So to find the probabilities for each of these sample proportions, we will take each number of outcomes and divide it by the total possible outcomes. So for a sample proportion of 0, there is 1 outcome, and we divide this by the total number of outcomes, which gives us a probability of 1 out of 8. For a sample proportion of 1/3, there are 3 possible outcomes, so its probability will be 3 out of 8. For a sample proportion of 2/3, there are 3 outcomes, and we divide this by 8. And then for a sample proportion of 3 out of 3, there is 1 outcome, and so its probability will be 1 out of 8. And so this is the sampling distribution for the sample proportion that prefers Coke. So now let's find the mean and the standard deviation of the sampling distribution. So here we're going to let our random variable x be the proportion that prefers Coke. And so to find the mean, or the expected value of our random variable, we take the sum of x times p of x. So here x is the sample proportion, and p of x is the probability. And so we calculate the mean by taking each sample proportion and multiplying it by its corresponding probabilities, and then we add them together. So we have 0 times 1 out of 8 plus 1/3 times 3 out of 8 plus 2/3 times 3 out of 8 plus 3/3 times 1 out of 8. So simplifying, we have 0 plus 1 out of 8 plus 2 out of 8 plus 1 out of 8. And this will give us 4 out of 8, which can be simplified to 1/2. And so the mean of the sampling distribution is 1/2. Now to find the standard deviation, we first need to determine the variance, and then we take the square root of the variance to give us the standard deviation. So the variance of our random variable is given by the sum of x minus mu squared times p of x. So we take the value for each sample proportion, we subtract the mean, square it, and then multiply it by its corresponding probability. So the first term we have 0 minus the mean, which is 1/2, squared times 1 out of 8 plus 1/3 minus 1/2 squared times 3 out of 8 plus 2/3 minus 1/2 squared times 3 out of 8, and then we add 3/3 minus 1/2 squared times 1 out of 8. And this will give us 0.083 repeating. And so now we can find the standard deviation by taking the square root of the variance. And so the square root of 0.083 repeating will be approximately 0.29. Under certain assumptions and conditions, we can actually model the sampling distribution for proportions. As long as the sample size is large enough, then the sampling distribution model for proportions will be normal, and it will have a mean that will be equal to the true population proportion P, and its standard deviation will be given by this formula. So here we use this notation SD bracket P hat to denote the standard deviation of the sampling distribution for a proportion. And you might see the notation sigma with a subscript of P hat. And the formula is the square root of P times 1 minus P, all divided by n. And so this will give us another way of calculating the standard deviation for the sampling distribution. And so if you go back to our previous example, if we were to calculate the square root of P times 1 minus P divided by n, so P is the proportion that prefers Coke. And so since we assume that half of the population prefers Coke, then P will be equal to 1/2. And so if we take the square root of 0.5 times 1 minus 0.5 divided by the sample size, which is 3, then this will give us approximately 0.29. And the mean of the sampling distribution is equal to the population proportion P, which we assumed to be equal to 1/2. Now, before we can use any model, we need to check whether certain assumptions and conditions are true. There are two assumptions that we need to make. The first is the independence assumption, where the individuals in the sample must be independent of each other, meaning that the outcome of one individual should not affect the outcome of other individuals. The second assumption is the sample size assumption, which says that our sample size must be large enough. Now, it is rather difficult to know whether an assumption is true or not, but we can check certain conditions about how the data is collected to determine if the assumptions are plausible. So the conditions related to independence are the randomization condition and the 10% condition. For the randomization condition, we want to make sure that we have a random sample from a population and random assignment to treatment groups if we are performing experiments. If the sample isn't random, then the sampling method has to be at least not biased, and the sample is representative of the population. The 10% condition says that our sample size should not be larger than 10% of the population. If we sample more than 10% of the population, then the remaining individuals are no longer independent of each other. And now the condition that corresponds to the sample size assumption is the success and failure condition. This condition says that we should have at least 10 successes and 10 failures in the data. And so mathematically, we can write this as n times p hat and n times 1 minus p hat as the number of successes and failures respectively. And these both have to be greater than or equal to 10. So here we define success to be some aspect or feature that we are interested in observing, and a failure means that we don't observe this aspect or feature. So for example, if we are tossing a coin, then we can define a success to be heads, and this would mean that tails would be the failure. Now, if these assumptions and conditions are satisfied, then sampling distribution for a sample proportion will be a normal curve. The mean of the distribution will be equal to P, which is the population parameter, and the standard deviation is given by this formula. We can use standardization to find the probability for a sample proportion by using the z-score formula for the sample proportion. So we take whichever sample proportion that we're interested in, we subtract the mean of the sampling distribution model, which is equal to P, and then we divide this by the standard deviation of that model, which is given by this square root formula. So let's look at some examples of how the sampling distribution models are used. According to Nestle, packages of Smarties contain 18% blue candies. Suppose we randomly select 100 of these candies. So what percentage of candies should we expect to be blue candies? So first, let's look at the assumptions and conditions for using a normal model for the sampling distribution. So the first is the independence assumption. So here the colors of the candies should be independent of one another. And now let's check the related conditions for independence, which are randomization and the 10% condition. So we are selecting the candies at random. So we have a random sample. So the randomization condition is satisfied. The other condition is the 10% condition, which says that our sample size should not be larger than 10% of the population. So here we assume that Nestle will produce a lot more than 100 candies, and so this condition is reasonably satisfied. So next we will look at the second assumption, which is the sample size. And so the sample size must be large enough and so we check the related condition, which is the success and failure condition. So this condition says that we need to have at least 10 successes and 10 failures in our sample. So here we have a sample size of 100, and P, which is the proportion of blue candies, is equal to 0.18. And so we calculate the number of successes by taking n times p, so 100 times 0.18, which gives us 18, and this is larger than 10, and the number of failures is calculated by n times 1 minus p, which is 100 times 1 minus 0.18, and this gives us 82, which is also larger than 10. And so the success and failure condition is met, so we can assume both independence and a large enough sample. So we can assume that the sampling distribution model is going to be normal. It will have a mean which is equal to the proportion of blue candies, which is 0.18. So this is our expected value, and so we expect 18% of the candies to be blue. So now what is the standard deviation? Well, the standard deviation of the sampling distribution model is given by the square root of p times 1 minus p divided by n. So p is 0.18, and we have a sample size of 100. So we take the square root of 0.18 times 1 minus 0.18 all over 100, and this will give us approximately 0.03841 0.87454246. And I'm writing all of these decimals here, which will be used in the next part. And so this is our standard deviation. So now, what is the probability that a random sample will contain 24% or more blue candies? And so here, let's use our model to determine the probability. So here we assume that the sampling distribution model is normal. The mean is at p, which is 0.18. So this is the proportion of blue candies. And we want the probability that a random sample will contain 24% or more blue candies. So 24% as a decimal is 0.24. So that is our sample proportion. And to find the probability that our sample contains 24% or more blue candies, then we will want to determine the area to the right of 0.24. So rather than working with this normal model, let's look at standardizing our data like we've done in previous examples by using a z-score transformation. So the z-score transformation is p hat minus the mean, which is p, divided by the standard deviation of our sampling distribution model. So the z-score for our sample proportion of 0.24 is 0.24 minus p, which is 0.18, divided by the standard deviation, which is 0.0384, and so on. So here we want to use as many decimals as we can for the standard deviation. And this will give us approximately 1.56, rounding to 2 decimal places. And so now we can work with the standard normal curve, which has a mean of 0 and a standard deviation of 1. And so we determined that our z-score was 1.56. And so finding the area to the right of our sample portion of 0.24 is the same as the area to the right of a z-score of 1.56. And so mathematically, we want the probability that our sample proportion contains 24% or more blue candies, which is the same as the area to the right of 1.56 in the standard normal curve. And because our z-table only gives us left areas, we need to use the complement rule to determine the area to the right. So we take 1 minus the area to the left of 1.56. So using our z-table, we find that the area to the left of 1.56 is 0.9406, which means that the area to the right is going to be 1 minus 0.9406, which is 0.0594. So the probability that a random sample contains 24% or more blue candies, is 5.94%. Now let's take a look at the next example. When a truckload of apples arrives at a packing plant, a random sample of 150 is selected and examined for bruises, discoloration, and other defects. The whole truckload will be rejected if more than 5% of the sample is unsatisfactory. So let's suppose that 8% of the apples on the truck do not meet the desired standard. So what is the probability that this shipment will be accepted anyways? So let's first look at the assumptions and conditions for using a normal model. So we have the independence assumption. So here we're looking at the defects of apples. And so we assume that the defects of an apple does not affect the defects of other apples. So they are independent of one another. So the two related conditions were randomization and the 10% condition. So here we have a random sample of 150 apples. And so this condition is met. The 10% condition, our sample size cannot be larger than 10% of the population. So here we're considering the entire truck to be the population, and we assume that the truck has at least 1,500 apples. And so this condition is reasonably satisfied. Now the next condition or assumption is the sample size. So we need to have a sufficiently large sample. And so we check the success and failure condition. And so our sample size is 150, and P is the proportion of defective apples. So we're given that 8% of all apples in the truck are defective, and so P is equal to 0.8. So we calculate the number of successes by taking n times p. So 150 times 0.08, and this will give us 12. which is greater than 10. And the number of failures is n times 1 minus p, which is 150 times 1 minus 0.08. And this gives us 138, which is also greater than 10. And so the success and failure condition is satisfied. So we can assume that we have independence and a large enough sample. So now we can use the normal model to find the probability that the truckload will be accepted. So let's first draw the model. We have a normal model, which is centered at P, so the proportion of defective apples, which is 0.08. We're given that the truckload will be rejected if more than 5% of the sample is unsatisfactory, which means that the truckload will be accepted if 5% or less of the sample is defective. And so we want to find the probability that our sample proportion is 5% or less. And so 5% as a decimal is 0.05. And so as long as our sample proportion contains 5% or less defective apples, then the truckload will be accepted. And so to find the probability, we want the area to the left of 0.05. And so this will give us the probability that our sample proportion has 5% or less defective apples. So let's first find the standard deviation of this sampling distribution model, which was the square root of p times 1 minus p divided by n. So p was 0.08, and our sample size is 150. So the standard deviation is the square root of 0.08 times 1 minus 0.08 all over 150. And this will give us approximately 0.0222 and so on. So you want to keep as many decimal places as you can for the standard deviation. And so now let's standardize our data so that we're working with the standard normal curve. So the z-score is p hat minus p divided by the standard deviation. So we have p hat, which is 0.05, minus p, which is 0.08, divided by the standard deviation, which is 0.0222. And this will give us a z-score of negative 1.35, rounding to 2 decimal places. So now we can determine this probability by looking under the standard normal curve and finding the area to the left of our z-score of negative 1.35. And so the probability that our sample proportion has less than 5% defective apples is the same as finding the area to the left of a z-score of negative 1.35. We look up negative 1.35 in our z-table. We find that the area to the left is 0.0885. And so the probability that the truckload of apples will be accepted is 8.85%. So the mean of our sampling distribution is equal to P, which is the proportion of people that do not make payments on time, which is 7%, so 0.07. We have a sample size of 200, and so the standard deviation is going to be the square root of P times 1 minus P all over n. So we take the square root of 0.07 times 1 minus 0.07 all over 200, and this will give us approximately 0.0180. So now, what are the assumptions that underlie the model and which conditions are met? So we have the independence assumption, and so we assume that the clients make payments independently of each other. Now we look at the related conditions, which are randomization and the 10% condition. And so we should assume that the sample is random, or at least representative of the population. The 10% condition says that our sample size should not be larger than 10% of the population. So we assume that our sample size is not larger than 10%. Our other assumption was the sample size, so we need to have a large enough sample and so we check the success and failure condition. So we calculate n times p and n times 1 minus p. So we have 200 times 0.07, which is 14, and we check n times 1 minus p, which is 200 times 1 minus 0.07, and this gives us 186, which is also greater than 10. So the condition that is satisfied would be the success and failure condition. Now, what is the probability that the clients do not make timely payments? So here we're going to use our normal model. And the mean is equal to P, which is 0.07. And from part B, we're given that the standard deviation was approximately 0.018. So to find the probability that more than 10% of clients do not make payments on time is given by the area to the right of 0.1 and so we will first look at finding the z-score. Which is given by p hat minus p divided by the standard deviation. So we take 0.1 minus p, which is 0.07, over the standard deviation, which is 0.0180. And this will give us approximately 1.66, rounding to 2 decimals. And so now we can look for this area under the standard normal curve. And so the probability that more than 10% of our sample will not make timely payments is the same as the area to the right of 1.66 under the standard normal distribution. And because we want the right area, we will use the complement rule and take 1 minus the area to the left of 1.66. Looking up 1.66 in our Z table gives us 0.9515. And so the area to the right is going to be 0.0485. So the probability that more than 10% of clients will not make timely payments is 4.85%. And so this will conclude our lesson for this video. In the next video, we will talk about the central limit theorem, as well as the sampling distribution model for means.